All right, so this could still be section 2.1. This is the second part of this video. So again, if I just look at a problem without reading the instructions, it doesn't tell me a lot. By just looking at this, I wouldn't really exactly know what to do. So as I read the instructions, the first instruction for each problem at 19 through 30 said plot each point. For problem 20, since I'm going to do that first, I'm going to plot the point 24. Easy enough to plot the point 24. I go 2 to the right and up 4. And then it has multiple parts. Then it says plot the point that is symmetric to it with respect to the x-axis. So this next group of problems is on symmetry. And every point has a kind of mirrored point that has a certain kind of symmetry. I want to plot the point that is kind of its mirrored image across the x-axis. And for the point 24, the point that is its mirrored image across the x-axis is the point that is exactly the same distance from the x-axis with the x-coordinate of 2. This point right here, the point 2, -4, we would say is its point of symmetry across the x-axis. So the point 2, 4 and 2, -4, we'd say these are symmetric about the x-axis because they have exactly the same distance from the x-axis and they're on the same vertical line that goes through the x-axis. So to create a point that is symmetric to another point, with respect to the x-axis, we just change the sign of the y-coordinate. And we leave the x-coordinate alone. So not going to be any algebra for problems 19 through 30. It's just to get used to the concept of symmetry with respect to x-axis, y-axis, and the origin. Part B of this says plot the point that is symmetric to the y-axis with respect to the y-axis. And to do that, I'm going to take the point and find its mirrored image on the other side of the y-axis, which is there. To do that, that's going to be this point, because these 2 points with respect to the y-axis are mirrored images of each other. And that, well, I didn't actually plot it right. And that point, which is right there, not right there, is the point -2, +4. Kind of overshot there. But that point, the -2, +4, these 2 points are equidistant from the y-axis, and they're mirrored images of each other with respect to the y-axis. And in general, to create a point that is symmetric to another point, with respect to the y-axis, we just change the sign of the x-coordinate. It's easy for me to see that these 2 points are kind of mirrored images across the y-axis, and that these 2 points are kind of mirrored images of each other across the x-axis. And that's what it means to be symmetric with respect to the x or the y-axis, that you're kind of the mirrored image across that axis. Part C, I'm not as visually gifted doing the next kind of symmetry. Part C says, then plot the point that is symmetric with respect to the origin. To get the point that's symmetric with respect to the origin, you change both the x and the y coordinate. So the x coordinate of 2 I'm going to change to -2. The y coordinate of 4 I'm going to change to the point -4. And this point right here, the point -2, -4, we say is the point of symmetry with respect to the origin, meaning that if I connect those 2 lines, those 2 points, with a line that goes smack dab through the origin, that they're kind of mirrored images of each other. Like here you have this line segment and that line segment will be exactly the same length. I hate to write this whole thing again, but I'm gonna. So the last thing I needed to do is plot the point that is symmetric with respect to the origin. I'm going to write something a little bit shorter. So to create a point that is symmetric to another point with respect to the origin, change the sign of both the x and the y coordinate. I'm out of room, so I'm abbreviating. So each of the problems between 19 and 30 won't have any algebra to do. They'll ask us to draw a coordinate system, and I printed those out so I didn't have to draw them, but you're just going to draw a crude xy axis and mark it up. So if you were doing problem 19, you'd just simply do this for 19. You'd first plot the point 1, 2. Good enough for the point 1, 2. For part A, symmetric to the x-axis, I changed the sign of the y. So this is going to be the answer to part 1A. I'll mark it as 1A. There's symmetric to the x-axis. For 1B, you're going to change the sign of the x, and you're going to get the point -1, 2, and that's the point that's symmetric to the y-axis. So I'll write 1B next to it. And for 1C, I'm going to change both the x and the y. I'm going to get -1, -2. That's going to be my answer to 1C. These points, the point 1, 2 and -1, 2 with respect to each other are symmetric between the origin. The point 1, 2 and -1, 2 with respect to each other are symmetric across the y-axis, and the point 1, 2, 1, -2 are symmetric about the x-axis. So for x-axis, if you want to find the point, you change the y. For y-axis, you change the x. That triangle means change. And for the origin, you change the x and you change the y. So each of the problems between 19 and 30 is going to be fairly easy to plot. So you might be able to go all the way through and do all the problems all the way up through 30, and that's completely fine. If you can't, you can watch me do them. So, problem 22, I'm going to start off by plotting the point -2, +5. So -2, +5 is my initial point. For part A, to find the point that's symmetric across the x-axis, I change the sign of the y in my answer to problem 22A. Oh, when I did yours, idiot, I wrote 1, didn't I? Let's see if I can find it. This is not 1. This was 19. And this was 19. And this was 19. Hardly matters, I guess. I had the wrong number there. But that should have been 19 that I was solving for you and not 1. It's just the first problem I'm doing in this video, so it felt like a number 1. Anyways, for 22a, the point that's symmetric to the point negative 2, 5 with respect to the x-axis, I change the sign of the y and I get the point negative 2, negative 5. For part B, the point that's symmetric across the y-axis, I change the sign of the x and I get the point positive 2, positive 5. So that's the answer for 22b. And for part C, I change the x to positive 2, I change the y to negative 5, I change both signs and get the point 2, negative 5. And that's going to be my answer to 22c. Again, for the x-axis, point of symmetry, you change the sign of the y. For the y-axis point of symmetry, I change the sign of the x. And for the origin symmetry, I change both the x and the y signs. And your answer is just going to look like that. There's no algebra to show. Way too many problems like this, but I'll do them because they go fast. So for 24, first I'm going to plot the point 5, negative 1. So there's my point 5, negative 1. Now to find the symmetric point across the x-axis, I change the sign of the y. That's going to be the point 5, positive 1. For the part B to go symmetric across the y-axis, I change the 5 to negative 5 and get the point negative 5, negative 1. And that's my answer to 24b. This was my answer to 24a. And for 24c, for the origin, I change the 5 to negative 5, the 1 to positive 1. I'm going to get this point here, and that's going to be the answer to 24c. That's the point of symmetry with respect to the origin. I don't need to draw any of the lines that I'm drawing that I drew in the first problem. 26, I start off drawing the point negative 2, negative 7. That's the initial point. For the point that's symmetric across the x-axis, I change the sign of the y from negative 7 to positive 7, and I plot the point negative 2, positive 7. This is the answer to 26a. That's the point that's symmetric across the x-axis. For part B, I change the sign of the x and get the point 2, negative 7. That's the point of symmetry across the y-axis. That's the answer for 26b. And then this point up here, I change the sign of the x and the sign of the y. They both go to positive. They go to the point 2, 7. And that's going to be the answer for 26c. That's the point of symmetry across the origin. '28's a little bit trickier because the point's sitting right on an axis. So for part A, or for the initial part of 28, I'm going to plot the point, and it's 4, 0. For 28a, I'm supposed to change the sign of the y-coordinate. And when I change the sign of the y-coordinate, I get the point 4, negative 0, because I'm changing the 0 to a negative 0. But negative 0 means the opposite of 0, which is just 0, or it means negative 1 times 0, which is just 0. So this right here, because negative 0 is the same as 0, is going to be the answer to 28a. So that's the original point. It's also the answer to 28a. For 28b, I change the sign of the x to negative 4, and I get the point negative 4, 0. So that's going to be the answer for 28b. And for 28c, I change the sign of the x and the sign of the y, so I get the point negative 4, negative 0. And that's the point as same as negative 4, 0, because negative 0 is the same as 0. So this point right here is also the answer to 28c. So when points are on an axis, the symmetry is a little bit trickier. '29 and 30. For 30, I'm going to plot the point 0, negative 3. For part A, for the symmetric point about the x-axis, I change the sign of the y. When I change the sign of the y, I get a positive 3, and the point turns into 0, positive 3. This is going to be my answer to 30A. That's the point of symmetry across the x-axis. For part B, the initial point is 0, -3. To find the point of symmetry across the y-axis, I'm supposed to change the sign of the y. I get -0, -3. -0 is the same as 0, so I get 0, -3. So the initial point is its point of symmetry with respect to the y-axis. If a point is on the y-axis, then there's no distinct point of symmetry. So this is also going to be my answer to, this was actually 30A right here. I wrote, oh, this was B. I did B. I didn't have to show any extra work. But for B, I did this right. I changed the sign of the x, and I get the same point. So my answer for 30B is going to be the initial starting point. For 30C, for the symmetry to the origin, I changed the sign of the x from 0 to -0, the y from -3 to +3. And again, that's going to be the same as the point 0, 3. And so this point 0, 3 is also the answer to 30C. So when points are on the axes, their points of symmetry can be a little bit, they're reflective, their points of symmetry with respect to the x-axis, y-axis, or the origin can be a little bit tricky. All right, so problems 31 through 38 are another bank of problems without any algebra. There's got to be a hiccup in the video because I'm cutting out my original lecture on problems 31 through 38 because I didn't like it. And as I started doing a lecture a few minutes ago, I didn't quite like what I said. So anyways, the instructions for problems 31 through 38 said determine whether the graph is symmetric to the x-axis, the y-axis, the origin, or none of the above. So what I'm supposed to do is look at the graph and decide which of these three symmetries it has, or if it doesn't have any of these three symmetries. That might be completely obvious without any explanation, but I feel obliged to do a little bit of explanation, and so I'm going to talk about what it means for a graph to have the different kind of symmetries that we're looking for. So there's three types of symmetries that we're looking for that a graph could have. The first one I'm going to talk about is symmetry to the x-axis. And basically a graph of a function, actually a graph, it's technically not even a function, a graph of an equation is symmetric to the x-axis if we can draw a line through the x-axis that would cut the graph into equal halves. So let me just make a random graph here that has symmetry to the x-axis, at least as symmetric as my cruddy drawing can make evident. I would say this graph is symmetric to the x-axis specifically because there's a mirrored image of the graph on either side of the x-axis, and per my instructions, if I draw a line across the x-axis, there's going to be the exact image above and below the x-axis. So if a line drawn through the x-axis creates two equal halves, one half above the x-axis, the other half below the x-axis, then that graph would have symmetry to the x-axis. To have symmetry to the y-axis, essentially the graph has to have equal halves on either side of the y-axis. And very specifically, if a line drawn through the y-axis splits the graph into equal halves, then the graph will be symmetric to the y-axis. So if I draw something like this, I would say this graph is symmetric to the y-axis, very specifically because if I draw a line down the y-axis, it's going to make two equal halves. The half to the right of the y-axis is symmetric to the half of the to the left of the y-axis. So just in case it's not clear, the first graph that I drew, it's symmetric to the x-axis because there's basically duplicate parts above and below the x-axis. This graph right here is symmetric to the y-axis because there's equal parts on either side of the y-axis. Those are the easy symmetries to see. This graph right here is not symmetric to the y-axis. For this graph to be symmetric to the y-axis, there'd have to be another part over here on the opposite side of the y-axis, so you'd have a mirrored image on the other side of the y-axis. So it's only symmetric to the x-axis. This graph right here is not symmetric to the x-axis, because to be symmetric to the x-axis, there need to be a part down here that was its mirrored image over the x-axis, for what that's worth. The third symmetry is a little bit tricky. The third symmetry is symmetry to the origin. And I say the graph of a function is symmetric to an origin if it looks the same upside down as right side up. And I'm going to construct a graph that's symmetric to the origin and show you how it looks the same right side up and upside down. And to kind of talk you through how I create a graph that's symmetric to the origin, I would like make a part of the graph, like maybe make a region of the graph in the first quadrant. To get this graph to be a graph that's symmetric to the origin, I have to double reflect. So if I want to create a graph that's symmetric to an origin, any portion of the graph that's in the first quadrant, I need to double reflect it. First, I need to reflect it over the x-axis to get that, and then I'll take the piece that I reflected over the x-axis and flip it and reflect it over the y-axis. I claim that this graph right here is going to be symmetric to the origin. And how can I tell by looking at a graph that's symmetric to the origin? It's not so hard, but it's the hardest of the tests. My test says a graph is symmetric to the origin if it looks the same upside down as right side up. And in order to show you that this graph is symmetric to the origin, what I'm going to do is I'm going to make a direct copy of the graph, and I'm going to flip it over for you. So this graph right here in red, I say is symmetric to the origin. So these are supposed to look the same. They kind of look the same. Watch what happens when I take this and I turn it over. When I take this graph and turn it over, these two graphs still look the same. If a graph looks the same right side up and upside down, we say it's symmetric to the origin. To create a graph that's symmetric to the origin, you need to take each piece, like the portion of the graph in the first quadrant, reflect it over the x-axis, reflect it over the y-axis to get it into the third quadrant. If I had to get a graph that's symmetric to the origin, like if I had a piece in the second quadrant, I could reflect it over the x-axis and then reflect it over the y-axis, and this graph all in red is going to also be symmetric to the origin, for what that's worth. But you don't need to be able to create graphs that are symmetric to the origin. You just need to be able to tell when a graph is symmetric to the origin, and the easiest way to do it is just to make a copy of the graph, flip it upside down. If it looks the same right side up as upside down, then it's symmetric to the origin. Alright, so now I'm going to start problems 31 through 38. For each of these problems, we're just supposed to say which of the symmetries it has, whether it has x-axis symmetry, y-axis symmetry, or origin symmetry. If it doesn't have x-axis, y-axis, or origin symmetry, we're going to say it doesn't have any of these symmetries. When I look at problem 32, it's very clear to me that it doesn't have x-axis symmetry, because to have x-axis symmetry, there need to be a portion of the graph beneath the x-axis that's a mirrored image of the graph. So it doesn't have x-axis symmetry. It's also clear to me that it does have y-axis symmetry, because if I draw a line through the y-axis, it creates two equal halves. So I know that this graph has y-axis symmetry. I know it doesn't have origin symmetry, because to have origin symmetry, the portion in the first quadrant would have to have a duplicate image in the third quadrant, and it doesn't. To check for origin symmetry, because I'm really not that gifted at checking for origin symmetry, basically what I do is I make a copy of the graph on a separate sheet of paper, and then I take that copy and I turn it upside down. If it looks exactly the same upside down as right side up, it has origin symmetry. But right side up, the parabola opens up. Upside down, the parabola opens down. Because it's not going in the same direction, it doesn't have origin symmetry. It doesn't look exactly the same. Of course, right side up and upside down, they're both parabolas, but they're not parabolas going in the same direction, so it doesn't have origin symmetry. So when I go to answer problem 32, 2, I'm going to say it has y-axis symmetry, it doesn't have x-axis symmetry, and it doesn't have origin symmetry. And because it has y-axis symmetry, I'm not going to use none of the above as an answer, because I only use none of these if it doesn't have any of the 3. All right, so 33 and 34 for me are also fairly easy. For 34, it doesn't have y-axis symmetry. In order to have y-axis symmetry, this piece right here would have to have a matching piece on the opposite side of the y-axis, which it doesn't. Similarly, a line that's drawn through the y-axis would have to cut it into 2 equal halves, and here the half to the left of the y-axis doesn't look like anything to the half to the right of the y-axis, so it doesn't have y-axis symmetry. It definitely has x-axis symmetry, because if I draw a line through the x-axis, I have an equal half on top and the bottom of the x-axis, so it definitely has x-axis symmetry. And to check for origin symmetry, I'm just going to sketch a copy of this graph, at least something that's vaguely like this graph. So this is about what this graph looks like. And I'm going to take this now and turn it over. And when I turn it over, now the parabola faces to the left as opposed to the right. To have origin symmetry, when you flip it over, it can't be going in an opposite direction. So it doesn't also have origin symmetry. It only has x-axis symmetry. My answer to problem 34 is the only symmetry that this has is x-axis symmetry. All right. For problem 36, if I want to talk about x-axis symmetry, it doesn't have x-axis symmetry, because like this piece down here would have to have a mirrored image up here to have x-axis symmetry, which it doesn't. Similarly, a line drawn through the x-axis, you'd have to have equal parts above and below the x-axis. And this part, although it's above the x-axis and it's the same look as it isn't directly above it, so we don't have x-axis symmetry. Similarly, we don't have y-axis symmetry because I'd have to have equal images on either side of the y-axis. On the left side of the y-axis up here, there's a graph. On the right side of the y-axis, I'm missing that extra graph that I need for y-axis symmetry. So there isn't a mirrored image on either side of the x-axis nor either side of the y-axis, but this one is going to have origin symmetry. If I take and draw just a really crude version of this graph, and I take it and I write it and flip it upside down, it looks just the same, at least, again, the same as my cruddy writing can make it look. So because it looks the same upside down as right side up, I'm going to say this has origin symmetry. And my answer to problem 36 is the only symmetry that this has is origin symmetry. So all your problems essentially have the same answer as my problem, so it shouldn't be hopefully too hard to get your problems done. And there's no algebra to do. Last 2 problems in this grouping, and then we'll get to a final grouping. For problem 38, it clearly doesn't have x-axis symmetry because there isn't a mirrored image of the graph beneath the x-axis. To have x-axis symmetry, there would need to be like a parabola beneath the x-axis. And to have y-axis symmetry, like this piece right here, would have to have a piece directly touching it on the opposite side of the y-axis. It doesn't have y-axis symmetry because if I draw a line through the y-axis, I get a little bit to the left of the y-axis and a big chunk to the right of the y-axis, and there's not a mirrored image on either side of the y-axis, so it doesn't have y-axis symmetry. And when I go to check for origin symmetry, if you can't visualize it upside down, I'm just going to make a pretty weak copy of this graph. This graph looks something like this. I'm going to turn it upside down, and when I turn it upside down, it doesn't look exactly the same because it gets flipped over and it doesn't go in the same direction. Because it doesn't look exactly the same upside down as right side up, it doesn't have origin symmetry. So it doesn't have x-axis symmetry, it doesn't have y-axis symmetry, and it doesn't have origin symmetry. My answer to problem 36 is the none of these. The none of these choice is reserved for any problem that doesn't have x-axis, y-axis, nor origin symmetry. So I'm going to cut this video and put it into the lecture, so you're going to get a hiccup coming out of this too. The instructions say determine which type of symmetry the graph of the equation has, if any. A graph of an equation will either have x-axis, y-axis, origin symmetry. It could have 2 or 3 of the above, or it might have no symmetry. And I'm going to do these problems in 2 steps. First, I will sketch a graph on my calculator so that I can make a guess at the type or types of symmetry. This isn't enough for a test. Once I determine the types of symmetry that I think it has, second, I'm going to perform the appropriate test to confirm my guess. So without a graphing calculator, you won't be able to make a guess at the type of symmetry, and there'd be a way to get an answer, but it's going to take 3 times as much work as what I'm going to do. So at some point this semester, you're going to want to have a graphing calculator. You might as well get it right now. They rent graphing calculators from the C building at GCC North, and this early in the semester you should be able to get one. What I covered up here is the tests that we need to do. So when the instructions ask me to determine what type of symmetry a graph has, if any, to figure out if the graph has x-axis, y-axis, or origin symmetry, I can graph, and my graph will let me suspect what kind of symmetry it has, but it's not the absolute guarantee. So if I come up with a graph and it looks like it's symmetric to the x-axis, what I'm going to need to do is, in my equation, replace the y with negative y and then reduce. And if it reduces to exactly the original problem, it has x-axis symmetry. And this won't make sense till I actually do it. Usually, a graph has x-axis symmetry when the equation has a y squared and no other y term. Usually, a graph has x-axis symmetry when the equation has an x squared and no other x terms, no x to the first power terms. Origin's a little bit trickier. Origin, it usually has origin symmetry when there's only odd powers of x and y and no constants. There are more cases than this, and this might be a little bit premature. But as you go through the section, you might want to have these in your mind. If I see an equation and I'm asked what type of symmetry does the graph have, if an equation has a y squared, I think it has x-axis symmetry. If an equation has x squared, I think it has y-axis symmetry. And if it has like an x to the first and a y to the third, or an x to the third and a y to the fifth, only odd powers of x and y, and no numbers other than the x's and y's, it usually has origin symmetry. All right, so getting back to problem 40, what type of symmetry? Does it have x-axis symmetry, y-axis symmetry, or origin symmetry, or none of the above? First thing I'm going to do is graph this on my calculator. To graph something on my calculator, I turn my calculator on, clear out any junk that's in here. Hit the y equals button. I'd been graphing something before, so anything that's in here I'm going to clear out. So if you had bunches of things in here, you just scroll to them, clear, clear, clear. And I'd like to enter y squared equals x plus 1. These right here are y equals and not y squared equals. I can't enter y squared, and in order to graph this on my calculator, I need to solve this equation for y. So my equation in problem 40 can't be graphed on my calculator. My calculator can't graph y squared. So I need to take this equation and solve it for y to make my calculator able to graph it. To solve for y, I'm going to use square roots. On the left-hand side, square rooting a y squared will leave me with a y. And on the right-hand side, if I solve with square roots, I have to use a plus or minus sign. By the way, this equation has a y squared. I think it's going to be symmetric to the x-axis. So when I get around to graphing this, I think I'm going to get a graph that's symmetric to the x-axis. In order to graph this on my calculator doesn't have a plus or minus sign. What I'm going to do is I'm going to enter y1 equal to plus square root of x plus 1 and y2 equal minus square root of x plus 1. So when the algebra for solving for y produces a plus or minus, you won't be able to graph one function to get the graph, because when there's a y squared, it kind of splits into two graphs. So in order to get a graph, to sketch a graph so I can guess the type of symmetry, I needed to solve the equation for y. This is the worst situation when there's a y squared. You can't just do this graph with one graph on my calculator. So now I'm going to enter second and x squared for square root. The x key is right below the mode. I hit x plus 1 parentheses, hit enter, and then for the second one, I'm going to hit the minus in the bottom of my calculator for my y2, and then second, and then x squared, and then x plus 1 again. This will produce a graph of y squared equals x plus 1. It's the only way my calculator can graph with a y squared is to split it into two graphs. And I have no idea what I graphed. I know what I graphed recently. I don't know what my window was. I'm going to hit my zoom button and go down to option 6 that says standard, because that will produce a window that's suitable. And that's going to graph this for me. Not that you can see it, but it looks like, well, the graph looks something like that. And so by looking at that graph, my guess is it's symmetric to the x-axis. My guess would have been that in general, because when there's a y squared, I think the graph's going to be symmetric to the x-axis. So I'm done with my first part of this. I sketched a graph. I guess that the graph is symmetric to the x-axis. So my guess is there's x-axis symmetry. If this was a test question and you stopped here, you're going to lose points, because that doesn't guarantee that there's x-axis symmetry. The guarantee that you need to do is you need to do the test for x-axis symmetry. The test to determine if an equation is symmetric, its graph is symmetric to the x-axis, is to replace the y with negative y and reduce. If it reduces to exactly the original problem, then the graph has x-axis symmetry. So the test that I'm going to perform in problem 40 is I'm going to take the original function, the y squared equals x plus 1, and now I'm going to do the x-axis symmetry test. And the x-axis symmetry test is to replace the y with negative y and reduce. So the first part of the x-axis symmetry test says replace the y with negative y. The second part, all in the same sentence, says and reduce. If it reduces to exactly the original problem, it has x-axis symmetry. So this is the test, replace the y with negative y, and I'm going to reduce. Negative y squared can be written as negative y times negative y. Negative y times negative y, two negatives multiply out to be a positive, two y's multiply out to be y squared. If I look at the original problem and I look at what the problem can reduce to when I replace the y with negative y, because it reduced to exactly the original problem. The graph has x-axis symmetry. So my answer to this problem is going to be the graph has x-axis symmetry. And if this was a test question, this is what I need to do. I need to see the second step. So to absolutely be sure that my calculator wasn't tricking me and it made it look like it was symmetric to the x-axis, but it really wasn't, I have to do the test to confirm x-axis symmetry. And that test is taking the y in the original problem, replacing it with negative y, and reducing. If it reduces to something that's different than the original problem, it doesn't have that symmetry. If it reduces to the original problem exactly, it has that symmetry. All right, so I'm going to move on to problem 42. Hopefully you gave 39 a go. And immediately when I look at the 42, when an equation has an x squared, I think it has y-axis symmetry. That's when it has an x squared and not a second x to the first power term. I think this has x-axis symmetry, y-axis symmetry should I say. And my first step, I will graph so that I can make a good guess at the symmetry. And for my calculator to sketch a graph, the equation has to be solved for y. This equation, x squared plus y equal to 2, I couldn't graph on my calculator. It's not solved for y. It's not terribly hard to solve it for y. I'm just going to minus x squared from both sides. On the left side, if I minus x squared, the x squareds cancel. I'm left with the y. On the right side, I can write minus x squared plus 2, or I can write 2 minus x squared. I make less mistakes on my calculator if the x is written second, if it has just a negative in front of it. So I'm going to make my graph now. I'm going to enter this in y1. So I turn my calculator back on, hit the y equals, hit clear, arrow down, hit clear to clear the stuff that I just previously graphed. Now I'm going to go 2 minus, which is by the plus key, and then x squared. And I could hit zoom standard, or I can just hit graph, and it'll give me the same window that I had before. Now when I look at this graph, it looks something like this. And that certainly looks symmetric to the y-axis. So my guess is that it has symmetry to the y-axis. So my guess isn't enough, but it's going to be the answer. Second, I need to do the appropriate algebra test to confirm the symmetry. And the appropriate algebra test, when I think a graph has symmetry to the y-axis, I replace the x with negative x and reduce. If it reduces to the original problem, I do have y-axis symmetry. I thought this was going to have y-axis symmetry because the equation had an x squared and not another x term. So now I'm going to do the appropriate test. The appropriate test is to replace the x with negative x and reduce. And it has to reduce to exactly the original problem. The original problem was x squared plus y equal to 2. My test is going to go place the x with negative x and see if it reduces to the original problem. So I took the original problem, did the test that I'm required to do. That's changing the x to negative x and simplifying. Negative x squared is the same as negative x times negative x. Two negatives multiply out to be a positive. Two x's multiply out to be x squared. Because this and this are equal to each other, the answer is going to be appropriate that I guessed on. And again, if this was a test question, you need to show this second step, which is really minor to show. There are 3 different tests, but they're all basically the same. So this graph is going to have x-axis symmetry, specifically because when I graphed it, it looks like it has x-axis symmetry, but more appropriately, when I replaced x with negative x and did just the minimal algebra, it reduced to exactly the same as the original problem. And that means it has x-axis symmetry. All right, so a few more problems. When I look at problem 44, the y has an odd power, the x has an odd power, and there's no numbers like that aren't part of, there's like a plus 7, you know, it's not like y equals 3x cubed plus 7. I would guess when there's only odd powers of x and y and no constants that it probably has origin symmetry, and I'm going to try to see if it has origin symmetry. So I don't need to do any algebra to solve it for y. So first, I'm going to graph so I can guess at the symmetry. So I'm going to graph y equals 3x cubed on my calculator. So y equals, clear the stuff that's on there, and type 3x, and then you have to use this up arrow key right above the divide to get an x cubed, and then up arrow 3. I've got an older calculator, so it doesn't make that exponent nice and elevated for me. And I'm just going to hit my graph button. So that graph looks something like this. Let me turn my calculator graph over and ask myself, does it look the same upside down as right side up? And it certainly looks exactly the same upside down as right side up. So I guess there's origin symmetry. And again, that's not going to be enough on a test. Second, I need to confirm my guess using the appropriate test. And the tests shouldn't be shocking, because at the beginning of this video, when we plotted the points of symmetry, to get the point of symmetry with respect to the origin, we changed the sign on both the x and the y. The test that we need to do for origin symmetry is the most complicated. We need to take the original function, change the x to negative x and the y to negative y, and then we have to do a little bit different reducing to get it to go back to the original problem. So the original problem is y equals 3x cubed. The appropriate test for origin symmetry is to change the y to negative y and to change the x to negative x and reduce. So I'm going to go negative y equals 3 times negative x cubed. And for me, it's going to help on the left side if I write negative 1y. And on the right side, I'm going to write negative x times negative x times negative x. And better yet, negative 1x times negative 1x times negative 1x for the x cubed. When I multiply the negative 1's together, I get a negative 1. So I'm going to get 3 times negative 1 for the cubing this, or negative 3, and x times x is x cubed. So this gives me negative 1y equals negative 3x cubed. And now I'm just going to multiply both sides by negative 1. I'm going to go negative 1 times negative 1y and negative 1 times negative 3x cubed. Negative 1 times negative 1y is going to be positive y. Negative 1 times negative 3x cubed is going to be positive 3x cubed. That's exactly the original problem, because when I reduced it, it reduced to exactly the original problem. Then the test is confirmed, and the answer to problem 44 is we have origin symmetry. So there's 3 different tests for symmetry. The test for symmetry to the x-axis, generally there's a y squared, and it's really easy to change the y to negative y, and when you have a negative squared, it turns into the positive squared. Similarly, the test for the y-axis is really easy too, because you're just changing a squared term to a negative squared term, and the negative just kind of works itself away. The origin symmetry is the icky one, because you're double negativing and you've got odd exponents, and it just makes it a bit of a mess. Generally on a test, I don't have a habit of putting origin symmetry, but I can. It doesn't mean I don't usually put it, but it doesn't mean it can't happen. All right, so just a few more problems. 46 is nice because I can go immediately into making my guess on what kind of symmetry it has. When I look at my little hints here, the equation doesn't have a y squared, so I don't think it has x-axis symmetry. It has an x squared, but in top of an x squared, it has an x to the first power term. And when you have both an x squared and an x to the first power term, that's not enough for it to have y-axis symmetry. I don't think this is going to have y-axis symmetry. And it has both even and odd powers of x. I don't think it's going to have origin symmetry. I think when I graph this, it isn't going to have any of the 3 symmetries. And if it doesn't have any of the 3 symmetries, there's no algebra to show which symmetry it has. I'll just say it doesn't have any of the symmetries. So let me go ahead and sketch a graph. That's step 1 on these. So step 1, sketch a graph so I can make a guess. And for this problem, I go y equals clear, and then x, hit the x squared key, minus 3x minus 4, hit my graph key. Looks something like that. It's not going to look the same upside down as right side up, because upside down it points down, right side up it points up, so it doesn't have origin symmetry. A line drawn through the y-axis almost cuts it into half, but the right half is bigger than the left half, so it doesn't have y-axis symmetry. And a line drawn through the x-axis, the top and the bottom don't look the same at all. So my guess is there's no symmetry, and because there's no symmetry, there's no test to confirm that there's no symmetry. I'd have to do all the tests and show that they fail. So my answer for this, I'm just going to say there's no symmetry. Doesn't have any of the 3 symmetries, and I'm not going to do any algebra for this. All right, getting close. 2 more problems to go. So problem 48 and 47, there's an x squared. I think it's going to have y-axis symmetry. So let me see if it has y-axis symmetry. It's already solved for y. I'm going to graph it. Step 1 in each of these problems is to make a graph to see if I can detect the symmetry. So I'm going to graph y equals x squared plus 6. I don't care that the y is on the other side. I hit graph. Graph looks like this. It had an x squared. I think it has y-axis symmetry. A line drawn through a better drawn graph would have perfectly cut it into 2 halves. So I think it has y-axis symmetry. So I need to do the test to confirm it. The test is to replace the x with negative x, and it has to reduce the original problem. So my guess is that there's y-axis symmetry. Now I'm going to do the appropriate test. The original equation in 48 is x squared plus 6 equal to y. I need to replace the x with negative x. So I'm going to go, does negative x squared plus 6 reduce to the original problem? Well, negative x squared is negative x times negative x. and negative times negative is a positive, x times x is x squared. So since that reduces to the original problem, the answer, my guess is correct because the test worked. I did the test and the algebra that I did reduced to the original problem. The graph has y-axis symmetry. Video's got a hiccup in 3 minutes, so I'm going to try to get this last problem done in 3 minutes. When I look at problem 50, I see a y squared. When I see a y squared, I think there's x-axis symmetry. I'm going to graph this, but in order to graph this, I need to solve it for y. To solve this for y, I'm going to add 3 to both sides and get y squared equals x plus 3. And then I'm going to square root plus or minus square root and get y equals plus or minus the square root of x plus 3. I'm going to graph y1 equals to the square root of x plus 3 and y2 equal to the minus square root of x plus 3, so I could make my guess. First step in all these problems, I'd like to make a guess at the answer. I guess I guessed already it was going to have x-axis symmetry, but I'd like to make my guess a little more accurate by doing the graphing. So now I yank out my calculator, clear what's in there, second and x squared for square root, and then x plus 3, and then negative on the very bottom row of my calculator, and then second and x squared, and then x plus 3, hit my graph button, look at the graph, looks like that. That certainly looks like it has symmetry to the x-axis, so I'm going to do the appropriate test. So my guess is x-axis symmetry. And the test for x-axis symmetry is to replace the y with negative y. So now I'm going to do the appropriate test. The original problem said y squared minus 3 equal to x. I'm going to change the y to negative y and reduce. So the appropriate test is to change the y to negative y. Negative y squared can be rewritten as negative y times negative y. And negative y times negative y comes out to positive y squared because that reduced to exactly the original problem. The appropriate test confirmed my guess, and the answer to problem 50 is the graph has x-axis symmetry. So that's the end of the first section. It's a long section, and it has definitely some new stuff. There's a bit of review in this chapter that will come up, not so much in the first section, but in some of the later sections. So hopefully you got through all 49 odd problems in this section. If you get stuck on anything, please come visit me and I can unstick you before you get to your test.